Hello everyone, and welcome to our first video on functions. So this is going to be largely a bit of review for pre-calculus, but we want to make sure that we've got a real solid grounding in certain topics related to functions before we move into the rest of our material. So that's going to help us make sure we interpret everything else in the future correctly. Let's start with a definition. So a set is a collection of distinct, that is, unique objects, and the objects in a set are called elements. So, for example, we have the set A, which is the collection of the objects cat, dog, and parrot. So those are three distinct elements. Set B has the elements 2, 3, 5, 7, and 11. Notice that this definition of a set does not restrict them to being numbers. Sets can be any collection of unique objects. And definition: a function is a rule that assigns each input of a set D, called the domain, to a unique output of a set R, called the range. Now, this second condition here, to a unique output of a set R, is the key thing that we want to think about when we talk about functions. So we'll elaborate on that momentarily. Now, one more definition. The input of a function is called the independent variable. The output of a function is called the dependent variable. So, I think the best way to visualize what's going on with a function, what makes a function special, is to consider a soda machine. So generally with a soda machine, what you expect is that each button that you press has one soda that it's going to spit out of the machine. So it might have multiple buttons that do the same thing, like you might have two cola buttons, you might have one lemon and one root button, beer, for example. So you might hit each of these buttons might spit out the same soda. That's totally fine. So that's two inputs with one output, not a problem. But what we don't want is a soda machine that isn't predictable. So if we look at this one on the left here, this is certainly a function. That's not a problem. But if we look at this soda machine on the right, well, here we have an issue because this button assigns that button press to two different outputs. If you press this button, you might get a cola or you might get a root beer. So this is not a function. And the problem here is the lack of predictability. What we want with a function is that this rule takes each input and gives it just one output. And without that predictability, the thing that we're describing is no longer a function. Personally, I wouldn't want a soda machine where when I hit the button, I got something random. I want to know what I'm getting out of my soda machine. So let's take a look at some other ways to visualize functions here. So we might use this sort of graph mapping where we have one set, the domain, and so this set is X, Y, and Z. And then we have the second set, the range. That's 1, 2, and 3. And we show with arrows the mapping between each input and output. So this function, its rule says that when you input X, you get out 1. When you input Y, you get 3. When you input Z, you get 2. Now when we look at this second function here, this mapping says that when you input A, you get cat. When you input B, you get dog. And when you input C, you get dog. Again, still a function. You've got two inputs that go to one output. That's fine. Not a problem. Now here, when we look at this is not a function because this rule says that the input 1 goes to do two different outputs, A or B. We don't want that. We want only one possible output for each input. So this is not a function. All right, so let's move on. Now we're going to introduce another term. This term's going to come back to being more important later, but we want to make sure we've got a clear understanding of what we mean when we say operation. So we use the term operation to refer to functions in particular contexts, such as addition, subtraction, multiplication, division. These operations have input pairs, like adding two numbers, with unique outputs. So, for example, when we talk about multiplication, that's a function of two inputs, X and Y, and the output is what you get when you take the product of those two things. Now, we'll worry more about operations later, but for now, let's consider another notation for functions, that of ordered pairs. So sometimes we illustrate a function by writing an ordered pair in the form x f of x, where x is the input, and f of x is the output. So this set of ordered pairs are here, a2, b5, c dog, apple bat, is a function. That's a function because each input, a, b, c, and apple, has one corresponding output, 2, 5, dog, and bat, respectively. Now, on the other hand, when we look at the set S, the input 1 appears twice with two different outputs, 2 and 4, so that would not be a function. Okay, here's another way to describe a function using a table. So here our input is the column on the left, and our output is the column on the right. So on the left, we have A, B, C, and apple. And on the right, we have 2, 5, dog, and bat. That means when you input A, you get 2. When you input B, you get 5. When you input C, you get dog. And when you input apple, you get bat. So you might notice that this is the same function we described up here in R, right? So identical functions, it's just two different ways of writing the same thing. Now, when we're talking about algebraic expressions, we usually define functions explicitly with a formula that relates the independent variables. So, for example, y equals x plus 2, y equals x squared, and y equals x minus 3 are all functions, meaning when you plug in a single x value, there's only one y value, one output that you can get for that, so that makes them functions. On the other hand, y squared equals x squared is not a function, and we can see that by just solving this for y. When I take the square root of each side, I get y equals plus or minus x, which tells me immediately that there's two possible answers for y for any given x value. If x was 3, y could be plus 3, or it could be minus 3. So that's two different possible outputs for the same input. That means that this expression is not a function. Now, another way that we illustrate functions is as graphs, where the values on the x-axis, that's our horizontal axis, represent the values of the independent variable, and the values on the y-axis represent the values of the dependent variable. So this here is a function because each input, each x value, only corresponds to a single y value when we look at the graph of the curve here. And on the other hand, when we look at this single x value corresponds to two different y values. So that means this is not a function. And one of the ways we typically think about testing a graph for functions, I'm sure this sounds familiar, is the vertical line test. So if you can draw a vertical line through a graph and it passes through more than one point, then it's not a function. If anywhere you draw a vertical line only passes through one point, then that is a function. Okay, so let's move on to talking about the domain of a function. So the way we talk about the domains of functions really changes based on the type of function we're dealing with. But when we describe the domain of a function, if it's not explicitly specified ahead of time, like you can artificially restrict the domain of a function. You could say, hey, I want to look at y equals x squared, but only for the domain x greater than 0. That's fine. But if we don't explicitly state the domain, then the standard convention is to use the largest set of real numbers for which the function can output real numbers. So that means you're checking what inputs make sense for the function that you're looking at. So what inputs make sense changes drastically based on the type of function we're dealing with. So let's take a look at this first example, f of x equals 1 divided by 4 minus x squared. So here, in order to figure out the domain, it's actually best if we think about what we can't do. Because when we're dividing, we know that we cannot divide by 0. So I might take this denominator and say, well, 4 minus x squared can't be equal to 0. So if I factor this using the difference of squares, I get 2 minus x times 2 plus x can't be equal to 0. And since a product of two numbers, if either one is 0, then the product is 0, this tells us that 2 minus x can't be 0, and 2 plus x can't be 0. So 2 cannot be equal to x, and x cannot be equal to negative 2. Okay, so that tells us what x can't be, but the domain is actually the description of all of the things x can be. So we want to put that in interval notation. Now, it might help if we draw a number line first, and we go, hey, when we look at negative 2 and 2, you can think of this as there's holes in the domain, and the domain is everything else. So these breaks at negative 2 and 2 tell us that we need to divide up our domain into 3 intervals, from negative infinity to negative 2. And make sure you use an open parentheses because the negative 2 isn't included. If it was a square bracket, that would mean it was included, but remember, we can't have negative 2 as a value here. And then this u means union with the next interval from negative 2 to 2. Again, make sure those are both open parentheses. Unioned with the interval from 2 to infinity. So in interval notation, this describes the set of all numbers except for negative 2 and 2. Okay, let's move on to another function. Now here, we've got a square root, and this is a little bit of a different story here. Because when we talk about the domain of a square root, we talk instead about what values we can have, right? So we say, well, you can't take the square root of a negative number, so that means your input must be, so 2x plus 1, must be greater than or equal to 0. It can be anything that isn't negative. And so if I just solve this inequality, I get 2x is greater than or equal to negative 1, which implies x is greater than or equal to negative 1/2. And that corresponds to the interval negative 1/2 to infinity. Okay, so let's take a look at another function here. So this one's a little bit trickier. So here we have a square root of this quadratic expression inside. And this would be pretty tough to solve the inequality directly, so we kind of use a little trick here. So we want x squared plus x minus 6 to be positive. But if I factor this quadratic, all right, so I'm looking for factors of negative 6 to add up to positive 1. That's positive 3 and negative 2. So here, I want the product of these two numbers to be positive or 0. Well, that means either both have to be positive or both have to be negative, right? So if we're multiplying two numbers, we know that we only get a positive if they're both positive or they're both negative. So we have two possibilities. Either x plus 3 is greater than or equal to 0 and x minus 2 is greater than or equal to 0 at the same time, or x plus 3 is negative or equal to 0, and x minus 2 is less than or equal to 0 at the same time. So let's consider this first case. If x plus 3 is greater than or equal to 0, then x is greater than or equal to negative 3, and x is greater than or equal to 2. So here, we just have to figure out where are both of these things true. And this is another case where if we draw a number line, it can help us interpret this properly. So we look at negative 3, and we look at 2, and we say this first one here, I'll draw in red, that should include negative 3 and everything bigger than it. And then we'll do the other one in green. So that should include 2 and everything bigger than 2. So I'm looking for where both of these statements are true. Well, that's when it's greater than or equal to 2. So we can simplify this statement by just saying, yeah, these are both true, when x is greater than or equal to 2. And in interval notation, that becomes the interval from 2 to infinity, but here I should be using a square bracket because 2 is included. Okay, so let's do the same thing here. X is less than or equal to -3, and x is less than or equal to 2. And again, I want to just draw that number line so I can make sure I interpret this correctly. And it only has to be a rough sketch of the number line. It doesn't have to be perfect. So x is less than or equal to -3, so it should include -3 and everything to the left of it. And then x is less than or equal to 2 should include 2 and everything to the left of it. And so now we're just looking at the overlap. Where are both of these things true? Well, both of these are true, starting at -3 towards the left. So that's when x is less than or equal to -3. Now keep in mind, you're not always going to get an overlap that's exactly like this. So drawing the number line really will help you interpret these things properly. I'll try to do a quick example of what I mean by that momentarily. Okay, so in this case, the interval should look like -infinity to -3. Now, if either of these pairs of facts is true, then the function up here, the input will be positive for the function, and then the square root will be fine. So that means if either of these intervals, if x is in either of these intervals, then the input that we needed was positive. So that means our input can be from either interval. So we actually need the union of these two things. If our input is in either of these intervals, it will work in our function. Now, I didn't do an explicit example here, but just off to the side, I want to illustrate that you might get something like when you draw your number line, say, we'll put 1 and 4 here. You can definitely get situations like this, where, say, you're going from 1 onward and from 4 backwards, and in this case, I've drawn 4 not included. So here I'd be looking at where is the overlap? Well, the overlap would be between 1 and 4, but not including 4, because we've got that open circle here. So in this case, you would call this interval 1 to 4, where 1 is included with a square bracket and 4 is open. So just keep in mind, you're not always going to get this overlap where you just get one of the two expressions you had before. You might have them pointing the opposite directions, depending on the circumstance, and in that case, you'd get something more like this interval here. Okay, so let's move on to talking about range. So the range of a function, well, when a function is defined by an equation, we say that y is in the range of f if the equation y equals f of x has at least one solution. That's basically just saying that your output y is something you can actually get from some x value. So here, what do we have? We have y equals x plus 2, so this is just a line. So when x is 0, you've got the y-intercept of 2, which we'll do a little refresher on that in a bit. And the slope here is 1, right? 1 times x plus 2. So that means if I was to go over by 1, then I would add 1 to my y value. So I would go up to 3. And 2 points is enough to draw a line, so we can see that the line looks like that. And what do we see about the range? It should be pretty intuitive that the larger our x values get, the bigger the y value gets. The smaller the x value gets, the smaller the y value gets. And this line goes forever. Lines don't stop. So that tells us immediately that the range for this is all possible values. So we would say that the range is -infinity to infinity. Now, for the second function here, I can look at this one a little bit more directly. So I'm going to kind of do two different approaches. One involves knowing the graph, and one implies just looking directly at the function, which is Actually, I think a little more straightforward. So what do we know? We know that if we square a number, we have to get at least 0 or a positive value. You can't get negative numbers when you square something. So if squaring something is bigger than 0, greater than or equal to 0, then if I subtracted 3, x squared minus 3 should be greater than or equal to negative 3. That's just subtracting 3 from each side, right? But this is my y value. So what I'm saying here is y is greater than or equal to negative 3. And so my range would just be described as negative 3 to infinity. Now, something that we're going to refresh more on in a later section is graphing of functions, especially using transformations. But we'll just kind of touch on that now and come back in more detail to that later. So if we look at y equals x squared, that's our basic quadratic graph. When x is 0, we get 0. When x is 1, we get 1. When x is negative 1, we get 1. So forth and so on. The graph for x squared looks something like this. So when I take y equals x squared minus 3, again, we're going to go over this in more detail later. All that does is take the previous y value and subtract 3 from it. So your whole graph, each point on your graph is just going to go down by 3. It's going to look like this. And looking at it in that way, we can see the same conclusion that we had before, which is that our y value, the smallest it can be is negative 3. So this is greater than or equal to negative 3. So you get the same conclusion for the range, regardless of which approach you take to thinking about the problem. Okay, so now we're just going to take a look at a graph of a function and interpret the domain and range from that graph. So remember, the domain is the set of all valid inputs here. So this graph starts at 0 and ends at 5, but it doesn't include the x value 2. There's no output on the graph here. That's what that open circle means, that there's no output value there. So that tells us we actually need to break the domain up into 2 intervals, from 0 to 2, with 2 not being included, unioned with the interval from 2 to 5. As far as the range goes, vertically speaking, there's no values that are missing between -1 and 3, except for 3 itself. That's the only place that the graph doesn't touch. So this is -1 to 3, and 3 is open. All right, so another couple quick reminders of some terms here. The x-intercepts of a graph are the x values where the graph touches the x-axis. In other words, that's the x values are where y equals 0. And the y-intercepts of a graph are the y values where the graph touches the y-axis. In other words, the y values where x equals 0. So we'll just draw a quick sketch here. So you've got some graph that looks like this. So here we've got 2 places where the graph touches the x-axis. And those are what we call the x-intercepts. And of course, notice that that's got to be, if it's crossing the x-axis, that's where y equals 0. So if you have the expression for the function, you can always find the x-intercepts by plugging in y equals 0 and solving. And similarly, here is our y value where the graph crosses the y-axis. So we call this the y-intercept. And notice again, this is where the x value is 0. So you can find y-intercepts in a function by plugging in x equals 0. All right, now we're just going to do a couple examples to kind of get warmed up to writing expressions using algebraic expressions, basically creating functions out of algebraic expressions. So here, the sum of two numbers x and y is 28. So let's just write that down. X plus y equals 28. Write the product p of these numbers as a function of x. So normally p is x times y. But what it's saying is, let's write this as just a function of x. So that means we need to get rid of the y here. Okay, well, how do I get rid of the y? Well, I can take my first relationship here and solve it for y. So this gives me y equals 28 minus x. And then I can take that information and plug it in to my product. And this becomes x times 28 minus x. All I'm doing here is saying y is equal to 28 minus x, so I can replace the expression y with 28 minus x, and it'll be the same thing. This gives us 28x minus x squared. So, writing that properly, that's p of x equals 28x minus x squared. And that's it. That gives us the product of the numbers x and y that add to 28, but written as just a function of x. Now notice, the only reason we can do this is because we have this constraint on the relationship of x and y. If we didn't have a constraint like that, you of course wouldn't be able to do any work like this. Okay, so let's go ahead and tackle one more example. A 300-foot cubed pool will be built with a square bottom whose side lengths are x. The sides are built with tiles and the bottom with cement. The cost of the tiles is $6 per foot squared, and the cost of the cement is $2 per foot squared. Write the total cost C as a function of x. So we've got a couple things we have to figure out here. So first of all, what does this relationship here tell me? 300-foot cubed pool with side lengths who are x. So let's go ahead and try to draw a pool here. So the bottom is square. Oh, I'm butchering that drawing. Let's try that again. No one said I was an artist. All right. That's significantly better. It's not perfect. Just imagine with me. Do your best. All right, so this side length is x. This is x. We didn't say what the height of this pool was, so we'll just give it our own label here. That's y. So now we want to figure out, okay, what does the 300 feet cubed tell us? Well, that tells us that the product of x times y is 300. Right? That's the volume. And volume of a rectangular prism is the product of each of the three dimensions. So the volume is x times y, or x squared y, and this is equal to 300. So, in other words, we could just say x squared times y equals 300. Now we want to figure out how to total up the cost of this thing. So the cost, well, what do we know? The cost of the cement is $2 per square foot, and the only part that corresponds to the cement is the bottom. And the area of the bottom is just going to be x times x. So we get $2 times each square foot for the bottom, right? So this is the area of the bottom. Plus $6 times the area of the 4 sides. So if there's 4 sides and each side has an area x times y, that means that the total area is 4 times x times y. So that's the area of the sides. Now the last thing we need to do, it says write the total cost function as a function of x. So that means we have to replace y, and that's where this constraint came in before. So we can say that y equals 300 over x squared. And now we can plug that in to our equation. So this is 2x squared plus 6 times 4 is 24 times x times 300 over x squared. That's 2x squared plus. Now, the x over x squared simplifies to just 1 over x. Now we have 24 times 300. 24 times 100 is 2400, times 3 is 48, 7200. Maybe check that with a calculator. All right, that's all I've got for you in this section. Thanks for sticking around. Have a good day.